So I've decided to make some videos that are about ideas that you can reuse. They're things that help our thinking, tools that are reusable, that they're judgmentally inert, right? They can be used to decompose ideas, and you'll end up using them to justify your ideas if they can be justified. And this is a way. So the two concepts are one, boundary conditions. This is used in physics, and steady state solutions. So for example, let's say you're hanging a rope between 2 points and you want to calculate, that sag that a rope has. What's the shape of that? I believe it's a cosecant if I remember correctly. But how would you calculate that? Well, when you're hanging the rope up, the rope's jiggling. It, calculating, as a function of time, the shape of the rope, you know, after you've hung it up and it's all jiggling, that's complicated. In fact, probably so complicated that even theoretically there would be problems trying to calculate it. There would be random, stochastic, unpredictable elements to it. So, what you can calculate though is what happens after all of that jiggling works its way out. Because of friction, the jiggling of the rope, it'll turn into heat, it'll do all kinds of things, and after a while, that energy will get spent and the rope will just be hanging there. And how would you calculate that? Now, especially since this is a real rope between two, it's from one side of the street to the other for hanging banners over the street, say. And if you're going to calculate that shape after, once it's in its steady state, after the friction has worked its way out of the system, and and mind you, those that initial state before the steady state, if your rope is of loosely woven leaves or something, it might break as you hang it because all the random jiggling, the extra pressure of when you're lifting it, could break it. Ignoring the initial conditions might be a problem. But let's say it's a strong rope. It can handle the torques and the uh, pressures and everything that it has to deal with in the initial states. And so you can calculate a steady state. And how you would do that is from one, its boundary conditions. So the boundary conditions for a rope are that each end is at a particular point. You get an XY for that point. And the steady state is, well, after these extra energies that you can't calculate have worked themselves out based on friction, based on thermodynamics, right? Based on every system that has a steady state eventually arrives at it. Um, you use these 2 points, the boundary condition, and the boundary condition is also involves the fact that there's gravity that's persistent, and you can calculate the steady state. What happens after all of the randomness works its way out? And as I was going to say, though, a weird thing about this is that, the wind is blowing, it's a real rope. So it's always waving and all kinds of crazy things are doing it. But you can calculate this hypothetical steady state, and in some cases, possibly contrived or simply constructed. Um, the steady state, if it's going to exist, can be thus calculated by the boundary conditions. So what we can take from this in general is every every analysis that you do has boundary conditions. So you need to find those boundary conditions. If this is a, let's say this is a pressured vessel, in which you're going to boil water or something under pressure, then the walls of that container are the boundary conditions. So there's always boundary conditions, and you should enumerate them. And then there's a steady state solution, which is, okay, after all of the uncalculable random perturbations work themselves out into a steady state. Another example, say you have a chamber. The boundary conditions being the edge of that chamber. The energy is contained within there. It isn't going to be let out. That's your boundary condition. And inside there, let's say you have cold spots and hot spots, and cold and hot. It's spotted. But there's an average temperature, right? But to start off with, there's these cold and hot spots. Well, you can basically wait for the steady state. What is the temperature after all the turbulence is mixed, all the gases in that chamber? What is the temperature going to be, right? To begin with, if you put a thermometer in at different points, you'd get different readings. But at the end, it's all mixed up, it's averaged out, and everywhere would be the same reading, which would be what? The average. So the steady state is that vessel will have a certain temperature, and wherever you measure it, it'll be pretty much the same. Even if it starts out that it's really cold on this side and really warm on this side, it'll mix up, and you'll have a steady state, which is what? The average. So the steady state is the persistent affects like gravity, like the fact that the rope is fastened at particular points, like the vessel has walls a particular shape, right? And this is a metaphor that we should apply to all of our analysis. There are boundary conditions. So if you want to tell me something and really convince me, you should be prepared to say when you calculated whatever you're trying to tell me, when you made your calculation, what were the boundary conditions that you assumed? Because that vessel has a boundary condition of, the vessel walls, but in reality, there's heat transfer. The rope has particular points, but in reality, the weight of the rope could move those points. If those points were held in place by springs, which everything essentially is, they would be stretched or whatnot. The boundary conditions are an assumption you make to be able to make your calculation. And the steady state is the same thing. The wind is blowing, the rope moves, but you want to know roughly what the shape, the ideal version of the shape of the rope is, and perfectly still wind and everything else. And that's also an assumption. So you check your assumptions by enumerating the boundary conditions, right? And then enumerating the forces that over the long run you think will express themselves, right? So if another example would be if in space there's some asteroid the size of the moon and it runs into the earth and it crushes in and they start spinning around. The actual motion of that particular collision would be very hard to calculate every detail. But after a while, you get into a steady state, and based on the energy that went into the system, you'll have a satellite orbiting at a particular distance at a particular time.